Welcome to this explainer. Today we're tackling a massive industrial challenge, separating chemical mixtures. You ever stop to think about how we actually get the refined fuels for our cars, or frankly, just guarantee the water we drink is perfectly clean? Well, it all boils down, sometimes literally, to these huge, fascinating processes running 24/7 behind the scenes in chemical plants around the world. Imagine trying to untangle a mixed liquid on a molecular level. It's an invisible puzzle, right? And solving it relies on some pretty strict laws of physics. We're talking towering metal columns, some of them are dozens of feet high, just packed with bubbling liquids and rising vapors. But how do engineers actually separate these invisible chemical bonds efficiently? Well, two major methods basically run the show here. To wrap our heads around this, we're going to frame this explainer as a head-to-head matchup between two engineering heavyweights, distillation and stripping. We'll quickly define the core concepts, look at the mechanics of heat versus gas, compare the actual column equipment, check out their energy use and applications, and finally, figure out how engineers choose the right process for the job. So, Part 1, defining the core concepts. Let's meet our contenders and break down their main mechanisms. In one corner, we have distillation. Formally, this is the separation of a volatile component from a liquid mixture by using heat. Think of it kind of like a boiling kettle on your stove. It purposefully uses an intense heat source to boil a liquid mixture. The absolute goal here is recovery. You want to capture that valuable, highly volatile component, the part that boils off first, basically, as your overhead product. You're intentionally cranking up the heat to extract the good stuff out of the top. And in the other corner, we have stripping. Stripping is the removal of a volatile component from a liquid, but instead of heat, you use a gas, usually steam or an inert gas. It's basically like taking a straw and blowing air through a liquid to push out unwanted bubbles. So rather than recovering something valuable, stripping is all about removing a less volatile or just flat-out undesirable component. You aren't boiling it, you're just using flowing gas to physically strip those impurities right out of the liquid stream. Moving on to Part 2, mechanics, heat versus gas. Now that we know what they're trying to achieve, let's look at the physical forces actually driving these processes. The starkest contrast here is definitely the energy source. Distillation relies entirely on intense heat. It uses a piece of equipment called a reboiler to generate vapor and recover that target product. Stripping, though, totally different game. It doesn't use heat. Instead, it injects a stripping gas to physically create that vapor phase and push the unwanted components out. So really, it's heat versus gas, recovery versus removal. But even with those huge differences, both processes share this one universal dynamic. It's basically the golden rule of mass transfer. Gas or vapor always flows up, and liquid always flows down. Picture the inside of these towering metal cylinders. You've got liquid cascading down from the top, while gas or hot vapor is aggressively rising up from the bottom. And this countercurrent flow, that's where the magic happens. The rising gas interacts with the falling liquid, transferring mass and actually separating the components, whether you're distilling or stripping. All right, Part 3, comparing the column equipment itself. If we were to peek inside these actual industrial columns to see where this liquid and gas interact, we'd see that because they operate so differently, their internal structures are practically opposites. Since distillation boils liquid to capture a valuable vapor, it absolutely has to have a reboiler at the bottom for heat, and a condenser at the top to catch and cool that valuable vapor back down into a liquid distillate. Stripping, however, is built completely differently. Because it relies on injected gas, it just skips the reboiler entirely. It uses a gas distributor at the bottom instead, and since it's just pushing out waste gases, it usually doesn't even have a condenser at the top. The unwanted vapor is just simply vented away or sent off to be treated elsewhere. Which brings us to Part 4, energy use and applications. We've got different physics, different structural designs. But how does that actually translate into real-world efficiency and specific use cases? The crucial thing to understand here is the energy footprint. Distillation relies heavily on constant, intense heat generation to just continuously boil industrial volumes of liquid. Because of that, its energy consumption is massive. Stripping, by contrast, generally boasts a much lower energy footprint. You're really just running a compressor to pump steam or inert gas through a distributor, and that requires vastly less energy than keeping a gigantic reboiler firing at those super high temperatures. Now, you might be wondering, if distillation eats up so much more energy, why even use it? Well, that hefty energy cost is easily justified when your end goal is a high-value purified product. Distillation is the undisputed king of producing refined distillates. If you need to extract pure ethanol, purify water on a massive scale, or process light hydrocarbons to make the gasoline that goes in your car, you absolutely need the thermal recovery power of distillation. The value of what you recover more than offsets that giant energy bill. Conversely, stripping is the highly efficient go-to choice for things like environmental cleanup and industrial safety. Because it effectively pushes out unwanted gases using way less energy, it's perfect for stripping hazardous volatile organic compounds, or VOCs, right out of wastewater. It's also the standard way to remove toxic dissolved gases like ammonia, highly dangerous hydrogen sulfide, and carbon dioxide from liquid process streams. You're not trying to make a profitable distillate here, you're just efficiently cleaning undesirable elements out of a liquid stream. And finally, Part 5, choosing the right process. Bringing this all together, how do engineers actually make the call when designing a multi-million-dollar chemical plant from scratch? It really all boils down to this one fundamental question. Are you going to spend more energy to recover exactly what you want, or are you going to use gas to efficiently remove what you don't? The choice between distillation and stripping is truly a masterclass in industrial efficiency. Engineers have to perfectly balance that immense energy cost of boiling a mixture against the desired purity of their final product. Basically, distillation recovers the gold while stripping takes out the trash. So I encourage you to think about these invisible, massive scales next time you fuel up your car or drink a perfectly clean glass of tap water. There's a towering column of cascading liquids and rising vapors out there that made it all possible. Thanks for joining me on this explainer, and keep questioning how the world around you actually works.